Hello everyone, I hope you and your family are doing well. I am Gyanendra Kumar Sa. I am currently doing my PhD in University of Rostock. As I have already explained in my previous videos that I am going to make a series of videos which will help you understand cascaded control design for DC-DC converters. This is fourth video in series where we will learn how to implement, validate our proposed inner current control loop using MATLAB Simulink environment. Here I have listed the 5 lectures which I'm going to prepare and upload to YouTube. So the main objective of these videos is to help you understand designing of inner current control and outer voltage control loops in cascaded form for DC-DC converters. So this is the fourth video where we will simulate our proposed inner current control loop, and we would also like to validate our control loop tuning. So the prerequisite for this video is to watch lesson 1 and lesson 2. So you should watch the lesson 1 and lesson 2 before proceeding with this video, because we are going to validate our control proposed in these 2 lessons. So in these 2 lessons, we proposed our inner current control loop in continuous and discrete time domain. Watching lesson 3 is also recommended, but it's optional. So you can avoid also watching lesson 3 if you have less time. But if you watch it, then it's also advantageous. Let's dig into our topic then. So the contents which we are going to cover in this lesson are discussion of Simulink models. So I have prepared a Simulink model and some MATLAB scripts which are going to be helpful to understand the implementation of current controller. And in the second part, we would like to see the step responses. So this is our time domain plot. So time domain plots. And then in the last part, we would also like to validate the current controller using closed loop command tracking plot. So where we would plot our Bode plots, and this is our frequency domain plot. Okay, so these are the main contents for this video. So here, as I said, I have already prepared the MATLAB model and MATLAB scripts which you can download. So this is the link where you can download the files, and let's download it together. So I'll just show you that how you can download this. So you just go copy the website and paste in the browser, then you can download from here. And now my file is downloaded. So I can go to my downloaded file, and then I can so you can see there in this file there are multiple files. So, and I'm currently using MATLAB 2020 B version, but it might happen that you do not have the higher version. You have some lower version. For example, you may have 16B. Then I have also tried to save the models with a lower version. So you can you feel free to open the model which you can use in your MATLAB which you have in your laptop. Okay, so you can basically copy these and just put wherever you want. So I'll just create a folder. You can extract it also. So you can do whichever way you want. Okay, so ICC validation. ICC means inner current control loop validation. Okay, and then you can open MATLAB and copy this address. So let MATLAB open. And then we place the address which we copied, and then you will see already the MATLAB files which was uploaded in the Google Drive. And this is the file where we have a lot of parameter initializations and then some calculations to get our plots. And this is the main model I'm going to open because my MATLAB version is 2020B. So let's open that. So don't worry, I will explain all these parameters or what they are doing, and you can also have a look. You can also have a detailed look when you download the model and you look through by yourself. Okay, so this is how our model looks like, and so let's see. So let us see first presentation. So there I have taken some screenshots so to explain the model, and then we will come back to the model again. Okay, so this is the file which we saw in MATLAB Script. So here we have initialized some variables. So the switching frequency we are going to use is 4 kilohertz, and this is our switching time period. And then so these are just some parameters. So again, I would like to mention that this is just one parameter example I have taken for my control implementation, and these are randomly taken. So you can choose these parameters the way you want, or basically you can choose the same parameters which you have designed your DC-DC converters. So I have considered that the output voltage of all three converters, buck boost, and our boost converters are 1000 volt. So this is our 1000 volt as output voltage for all converters. And the rated power I have assumed is 100 kilowatt. So for high power application, so not necessary. It should be for high power. It can be for low power also. And this is now sampling the Simulink sample time. So here I have tried to take the Simulink sample time 500 times less. So this make so you can choose this Simulink sample time as less as possible. And the more less value you take for the sample time, so the better simulation you get. So I have chosen like 500 times to get the plots nice. But if you want to run your Simulink faster, then you can for sure choose also TSW over 100. So it's like 100 samples in one switching time period. Yeah, but it's up to you. But I like the 500 because I was getting nicer results with the Simulink, and of course, when you reduce further and further, then your waveform also looks better and better. Yeah, so I choose this 500 by hit and trial, so that my waveforms were looking like the smoother and nicer. Okay. Okay, and now then these are the source voltage for DC-DC converters. So you can see for my buck converter, I have chosen 1500 volt. For boost converter, source voltage as 600 volt, and for the buck boost converter, 800 volt. Again, these are randomly chosen. You are free to choose any voltage you would like to choose. And just to design our inductor in the DC-DC converter, so I basically have some design parameters, and then how these are the well-known duty cycle computation equations, and then you can design your inductor parameter. So these are our inductor parameters, I would say, the inductance. So this is our L value, and this is the internal resistance of the inductor. And here I have randomly chosen this as 0.1 ohm. So this can be any value, like this is your inductor internal resistance. So I choose this 0.1 ohm. You can choose like 10 milliohm or 500 milliohm depending on your inductance rating. Okay, so these are about the parameters, the design parameters, and you can pause this video and look in detail also. Okay, so now it comes to PI tuning. So this is for our control tuning. So this is for our closed loop inner current control loop. And here we have some parameters. So this is the bandwidth which we would like to have, and our switching frequency is 4 kilohertz, and from thumb rule we know that our IBR, it's the like the safe value for our current control loop, the bandwidth can be less than or equal to the 10 times less the switching frequency. So in our case, it's going to be 400 hertz. So I have a result for two switching frequencies. So the first switching, I have results for two bandwidth tuning. So the first bandwidth is 100 hertz, and the second bandwidth I have is for 400 hertz. So we will see the Bode plot or the closed loop command tracking plot for these two frequencies. And for step response, we would use the 100 hertz. Okay. This is for step response. And then we have both for our command tracking plot. Okay, and as you can see, the sampling time for discrete time implementation. So I have already explained in my videos that for discrete time implementation, you can do double sampling. So this is basically your double sampling. So double sampling means if this is a carrier waveform, we sample the signals only at the upper or the lower extremes. So we do not sample any signals in between the extremes, and we just sample the signals at the extremes, and then we do our discrete time implementation. Okay, and this is about our PI tuning. So this is our PI tuning in continuous time domain. And we already know the expression. So our Kp is equal to omega Br into L, and Ki is equal to our Kp into R over L. Okay, so we know this expression, and for tuning the buck converter, I have used the buck converter impedance. For tuning the boost converter, I have used the boost converter impedances. And then for tuning the buck boost converter control, I have used the buck boost converter impedances. So this is in continuous time domain, and the same tuning in discrete time domain. So this is PI tuning in discrete time domain. And again, you can see the expression. So here the expression for K is 1 over 1 minus e power the T over tau divided by R. So this is our K. And so for each converter, I have computed the K. And then your Kp is equal to e power minus T over tau into 1 minus e power omega Br into T. And then the whole divide by K. Okay, so this is our Kp expression. And for Ki, what we have is, so we can also see from here, so it is 1 minus e power, so let me write down somewhere else. So I will write down here. So it's Ki is equal to 1 minus e power minus T over tau into 1 minus e power minus omega Br into T, then the whole divided by T into K. So these expressions we also saw in our lesson 1 and lesson 2, how we have obtained it. And for detailed look, please look the method 1 and like the lesson 1 and lesson 2. And here we have one simple variable. So this variable is command tracking plot on. So this so when this is 1, we would get you can just run this MATLAB script and it will run the Simulink model by its own, and then you can get your Bode plot at the end of this MATLAB script runs. Or if you make this 0, so we use this for step responses. Okay, so 0 means step response, 1 this variable equal to 1 means we can get the closed loop command tracking plot from this MATLAB script. Okay, So now you already saw this, that when we open the MATLAB model, the Simulink model, we saw this page. So here we have three converters. So we would like to compare our controls for all three converters which we proposed. So the one we have is buck converter, the second is boost converter, and third is buck boost converter. And here this is our reference signal. This is our reference inductor current, average current. So this is our reference average inductor current. And in this scope, you can see the average currents for all DC-DC converters, average inductor currents for all DC-DC converters. So this is for buck converter, this is for boost, and this is for buck boost. Okay. And in each scope, you see this reference average value, and then we have the average inductor in continuous time domain. So wherever you see underscore s, so let's say some text underscore s, this means in continuous time domain. Continuous time domain implementation. And whenever you see some text underscore z, so this means discrete time domain implementation. Okay, so you can use this notation to see whether we are implemented the control in continuous time domain or discrete time domain. And this is the reference signal which goes same to all the DC-DC converters. And in real world, we will have our voltage control loop. So this will be the output voltage reference, and then we will give the feedback we can give the feedback to our actual sample voltage, and then we have the controller. So this is our outer voltage controller, and this controller will give us the average inductor reference current. But since we just want to test our the current controller, so we have simplified our circuit by removing the output capacitor as a DC source, and hence we do not need to worry about controlling the output voltage, and hence we can only control the current, and then we generate this current reference. Okay, so this is a simplified way to check your current controller, but we will also see in upcoming circuit diagram why I generate this reference as like this. So here there is no voltage control implementation, we just have the current controller implementation. That is why we generate the reference inductor current as like this. So this part is basically our so until this part, this is our harmonics. So when I say harmonics, so this is equal to 10 times equal to sine of 2 pi f into t. Okay, so this is our harmonics frequency. So this is our harmonic frequency, and this is our DC value. Okay, so what we give as a reference as DC plus AC. So this is our harmonics, this is our DC value, and this is one variable which I described in the MATLAB script, that this decides whether you want to do a step response or you want to do the closed loop. You want to get the closed loop command tracking. So this signal, this reference, the upper signal which we use to get command tracking plot, and this lower reference signal we use to do a step response. Okay, so this is how this variable is playing. This variable is playing a role to just change the reference, whether to use harmonics in the reference or just to use the step as a reference. Okay, so this is about the reference and the converters. So now let's zoom into this. Let's open this buck converter and see how it looks like. Okay, before going there, these are the settings. So this setting is for our power GUI, and this is the setting for our Simulink configuration parameters. So here you can see I'm using the fixed step simulation, and then the fixed step size is our T Simulink, which was chosen to be 500 times less than the switching time period. Okay, so this is our if we open the buck converter, so this was our whole model, the main model, and when we open the buck converter, we see inside like this. And here you can see the current controller implementation in continuous time domain. So in upper part, you see the continuous time implementation, and in the lower part, you see this discrete time control implementation. And so you can pause this video and you can see how this the structure of this control looks like. So here you can see that this is our actual physical system. So this is our hardware. So from hardware, we can sample these currents and voltages. And you can see I have used this go to, from to and go to basically make the circuit looks nice in the Simulink. And you can see the same thing is coming here. Okay, so we find the mean of this. So this is our mean block, and then we give it as a feedback. And this is our PI controller. And this is our DID. So you can see the expression B. So here B is equal to minus V naught. And then you see this, we do 1 over A. So this is basically 1 over A. And this A is equal to basically Vs. And here we have this saturation block. So this is our saturation. So this, we know that the maximum range for duty cycle is from 0 to 1. So we would like duty cycle not to change within to not go above 1 and below 0. So we have this saturation, and whenever our the output of this controller goes above this the limits, and then what we would like to do is we would like to do anti-winding of integrator. So this anti-winding, so this part which you see here, this is your anti-winding. So anti-winding is very, very important. It's when you are implementing the control. So basically when you are out of the boundaries of the saturation block, then you would not like integrator to integrate some false value, right? So it's very important to disable our integrator when we are outside the saturation boundaries, so that our integrator does not accumulate some false value. And if you do not do that, so maybe in this implementation you do not see much difference, but believe me, it makes a huge difference to have anti-winding. Like I still remember in my bachelor's, then we were making a control for switch reluctance machine, and there we had forgotten to implement this anti-winding. And then what happened that I started the control, then we paused the control in between, and then we have given the speed reference as 500 RPM, but they still we have disabled the control, and of course the speed is the converter is not doing PWM, but our speed was 0, but I have not disabled the integration accumulation. So I should also disable the integrator, but it was not done. And since the error is positive, because the speed is 0, actual speed is 0, and the error is positive, and integrator value was keep on rising. So that is a one. And then next time I turned on my control, what happened is the integrator gave already very high value, and then boom. So my the speed of the motor went very high in a small time, and then everything tripped. So it's very important that you put some some anti-winding for this integrator, and this anti-winding you can do for your enable and disable signals for the control. And also whenever you have the saturation block, then also you should have this this anti-winding, so that your integrator does not accumulate some false values, or the values which is when our values are outside the boundaries. So you should be very careful implementing this, and you would see the importance of this anti-winding, especially in voltage output voltage control loop, where and when you want to implement when you want to operate in a safe region using this the saturation of average inductor current. So there you can actually see the difference in the implementation when you have anti-winding or you do not have anti-windings. Okay, so this is important, you should have it. So this is how the control was structured. So this is in continuous time domain, and in discrete time domain, as I said, we are doing double sampling. So this is our double sampling, and you can realize your double sampling using sample and hold block in MATLAB Simulink. And then we have this PI controller. So this is our PI controller, and again we have the expression A, which we divide, and then we have the expression B, which we do we subtract. So this is our DID, and this is again 1 over A. And then we have this saturation block again, and we do this carrier waveform and this is our PWM implementation. Okay, so this is our PWM implementation. And again, we have the same hardware circuit from where we sample the signals. So let's look inside this hardware circuit now. How does it look? So this is our buck converter, how it looks. So here we have the source. This is our source, and as I said before, we have our the load as a battery. So this is our battery. So I have changed the load as a battery voltage because we want to test our inner current control loop, and this is another application where you want to charge your battery using DC-DC converters. So I thought so there is a two advantage of replacing capacitor by battery. The first thing, we do not need to worry about output voltage control, and the second thing is we can also see how you can implement your control for charging your battery. And this is our normal circuit diagram, how the buck converter should look like. And then we get the PWM from converter, and then we give the switching signals to the switch S1 and S2. So for switch S1, we directly pass the PWM signal, and for switch S2, we get the complement of PWM S1, which we get as output from the controller. Okay, so that was about buck converter. This is about boost converter. So again, it's the same thing. Everything looks the same. We sample the signal, we find the mean, subtract, then PI controller. And here B is equal to Vs minus V0, and here A is equal to V0. Okay, so this is how the controller looks. But there is one interesting thing I would like to mention. So if you carefully see the upper limit of boost converter duty cycle, I have set it to 0.9. So there is a reason, because for the ratio between the output and the input voltage is equal to 1 over 1 minus D. And just imagine if duty cycle is equal to 1, then what happens? If duty cycle is equal to 1, your V out is going to be equal to Vs over 0, which is going to be infinite. So it is not a stable operating point. Okay, so D equal to 1 is unstable operation. Okay, so that is why you should limit your upper duty cycle to value less than 1, and so you can also decide this upper limit by your the maximum of safe duty cycle operation for your converter. So you are free to saturate your duty cycle at any value. I have chosen 0.9. You may also choose the upper value as 0.8 or 0.7. So it is your wish to choose these values. And again, we have the same thing, but in discrete time domain. And let's open the boost converter circuit. So now the boost converter circuit diagram looks like this. So you can again pause this video and get familiar with this circuit diagram. Okay, so this is our control design for buck boost converter. And here again, we have everything same. And you can notice again, the upper limit is not 1. Here we have 0.9. And you can see the V out over Vs is equal to D over 1 minus D for buck boost converter. And again, you can see D equal to 1 is unstable operating point. Okay. And I forgot to introduce that there are some scopes here. So you can, in this scope, you can see your the instantaneous inductor current, and then you can see the average reference current, and then the average actual current, and you can see the carrier waveform and duty cycle also. So this is for continuous time system, and for discrete time system, again we have another scope. So you can open these scopes and see the these parameters. So, and one more thing, that I have not used the mean block to compute the V out mean, because here it's just a DC, but you can for sure use another mean block also. Okay, but since it's a DC, so I have eliminated it. But for sure you can add a mean block also, and you can also expect some similar plots. Okay. This is our circuit for buck. This is not the boost converter, so this should be our buck boost. Okay. Yeah. So this is our circuit diagram for buck boost converter, and you can already see that the polarity of output voltage is reversed in this converter, and of course the direction of your output current is also reversed. Okay, which we also discussed in the lesson 1. So here now we have a step response, and so this is the step response where the ID. So this, you can see here different color, the labels or the legends, I can say. So the red one is our the reference average inductor current, and you can see the reference average inductor current is changed in a step format, and I cannot see the x-axis, so probably let's shift it above. So one moment. Yeah. Okay, so now we can see x level also, like x values. So x value is our time. So this is our time. And here we have the actual values in ampere. Okay. So these are the values in ampere, and here the reference value changes from 70 amp to minus 70 amp. And I would like to mention that you may think the DC-DC converter as only like where the power flows from source to load, but actually the power can flow from your load to source also. Okay, so this is your source. Okay, this is your source, this is your load. So so the power can either flow from source to load, or it can flow from your load to source also. So that is why, to show you that this control also works in those cases, so I have given the reference as positive, and I've given the reference as negative also. And you can see our closed loop current controller is tracking our reference currents for all the converters, for buck converter, for boost converter, and for buck boost converter. Okay, and here the bandwidth for tuning inner current control loop is 100 Hz, and let's verify whether it is correct or not. So this is the zoomed graph. This is the zoomed previous graph where we have given the step reference command as a 70 ampere, and so you can see our actual current change increases from 0, and this is all our average current so that it looks nicer. If it's instantaneous current, you will see some ripples over this and then it will go. So what we know now is we want to validate our bandwidth using step response. So there is a simple way you can do it. So what we know is the first order command tracking plot in S domain. So we saw something like this, omega br over S plus omega br. And if you find the command tracking like in time domain, so if you want to find the time domain response of this S function, so you would find something like, yeah. So this is your command tracking, and then this is equal to IL average actual S domain, and then this is your reference S domain. And if you try to solve this in time domain, this one, and using this as a constant reference, then what you can see is you can see the IL average in time domain is going to be it's going to be basically your so let's say this is your IM. So I say IM into 1 minus e power t over tau, okay. And here if you compare these two transfer functions, so what you can see is what you see is tau is equal to basically 1 over omega br. So that this is your time constant. Okay, so time constant for your closed loop command tracking plot in time domain, and of course you can find your time constant like this. So what we have is our omega br is 100 hertz. So we can solve it like this into 100. This will be equal to 1.6 millisecond. So I try to do the calculation beforehand. So it would come around 1.6 millisecond. So I try to see. So this is your 1.6 millisecond. And in 1.6 millisecond, we know that we have our this value is 63.2% of IM. Okay, so if our IM is 70 ampere, then we would have like 63.2% of IM at the time constant. And you can do the calculation. So 63.2% of your 70 ampere, it would be like so we can do the calculation, and so 63.2 into 70 divided by 100, so this is like 44.24. So this is like 44.24 ampere, and we can see here in this graph we have like the value is like 44.8, which is very close. And you can also see the actual value tracks smoothly the reference value. Okay, so this way what we can see is so this is very close to 44.81, and of course you can also see the delta t, it's like 1.61, so it's not exactly 1.6. So I can see that anyway, so this settings of the cursor I try to do manually by myself. So, and you can see our the bandwidth tuning is more or less accurate for is actually accurate for our current controller tuning. Okay, so this is a step response when there is a step from 0 to 70 amp. Now this is the step response when we have the reference signal changing from 70 amp to minus 70 amp. And if you see from here to here, the difference is 140 amp. And now if we see in one time period, so again this is our one time period. So I can draw like this. So this is time period tau. And in this case, what we would expect is that the voltage change from here until here is 44.81 into 2, because now the actual current difference from the starting and the steady state is 140 ampere. So yeah, so we would expect some current like this. So this would be like your 2, and then 6, 8, 9, and then we will have 8. So it would be like 80. Yeah, so from here until here we will have like the difference as 89.62. And then if you want to see in the actual value, then what you can do is you can basically so from so from here to here we have this, and then you can subtract this, you can subtract minus 140. So what we know is that from here until here, so let me use different color. Okay, so what we know is from here until here we have 89.62 volt, sorry, 62 ampere, and we would like to know the values with respect to this value with the reference of this x-axis, which is 0. Then for sure what you can do is you can subtract 70 out of this and then make the value negative. So once you do that, then what you would get this value as minus 19.62 ampere. Okay, and yeah, so you can do these mathematics by yourself, and you can verify these signals. And here also again when we see, so you can see that your delta, so delta t we know and delta y we expect as 89.62, and here we see like 85.34, so which is also close to our desired bandwidth. Okay, so these are the step response, and you can see the step response are actually nice, and they're exponentially going towards the steady state. Okay, so now let's talk about closed loop command tracking plot and how we can get these plots. So we saw in the first in the previous videos that we would like to get the Bode plot. So in Bode plot, the graph looks like this. So this is our gain. So gain is equal to the absolute value of your IL average and the IL average reference in S domain, or you can do in Z domain also. So Z domain means in the discrete time domain. And again, so this is phase plot, and which can be the angle of basically the same expression which we have above. So for sure these two may or may not be equal, so I would like to write OR. Okay, yeah, and then the x-axis is our frequency. Now and when we do the Bode plot, what we can expect for the first order system, we can expect some curve like this. So this here we have the gain 1, and then the phase curve like this. And we already know from our lessons that at bandwidth, which is FBR frequency, our gain is equal to 0.707, and phase is equal to minus 45 degree. But we would like to get these plots from our actual system. So okay, we saw the time domain step response, and we roughly calculated that our bandwidth is close to our design parameter. But now we would like to actually get this Bode plot, so we can verify the bandwidth of our system more accurately by getting this Bode plot, not from the step time response. Okay, so we would like to get this Bode plot. So how we get it? So there is a very simple way. So now let's draw the structure again. So we have this as a reference. So IL average reference value, then it goes to controller. It generates the duty cycle, and then it goes to PWM implementation, and that goes to your hardware. And then from hardware, we have the signals sampling. So this is our IL. This is our IL, and then we do the mean. Okay, so this is how it looks. So now, if you want to get the Bode plot and where the x-axis is frequency, so then you need to add harmonics into this reference value. So what we will do is we will realize our the reference average inductor current as DC plus AC. So here DC I have chosen as 70 ampere, and then AC is like 10. The magnitude is 10 ampere. It's just some harmonics or some disturbances I'm adding in the reference, and then we do this omega. So we do this 2 pi f into t. So here this f is basically your x-axis. X-axis in Bode plot. Okay, so this is how we can change the frequency in the reference signal. And what we do is we make a table. So we make one value as frequency. So we try to run the we try to add, let's say for one operating point I'm discussing, we try to add 1 Hertz disturbance in the system, and then we sample so then what we do is FFT. So you can do FFT of IL average. So yeah, so you can do FFT of IL average. So I would like to write it like this. So from FFT, if you are not familiar with FFT, so this is the processing of signals so that you can see the magnitude of the magnitude and the phase angle of a signal with respect to its frequency. So if you are not familiar with FFT, I would like you to visit MATLAB help for understanding how the FFT is implemented and how they look. So we would like to do FFT, and from FFT, basically we would like to see the gain of IL average, the actual value, and we would like to see the phase of the inductor value, the actual inductor current. And then again we would like to see the phase, the magnitude of the reference average inductor current, and then the phase of that reference average inductor current. So these green parameters you can get from your FFT. Okay, so you can do fast Fourier transformation and then you can get these values. And now you would like to see the gain and phase for the Bode plot. So these two are for Bode plot. So these for Bode plot. Okay. So what we do is we give one frequency, okay, and then we keep the signals to run for unless it gets the steady state operating point. Okay, so we give a single frequency harmonics into the system, and then we let the simulation run until we have reached the steady state point. Then we do the FFT of this. Then we sample the signals. We sample the actual signal. So this is for data logging. So we data log this reference value and the actual value into the MATLAB script. Okay, so we add one frequency in the system, then we do a data logging, and then we find these values of using FFT, and then the gain we calculate like this. So we basically know our IL average value and then IL star for our yeah, so which we got from FFT for this frequency, you know. So FFT will give all frequency gain and phase value, but we would like to focus on the gain and phase value for the harmonics frequency which is present in your reference value. Okay, so these gains and phase are for frequency F, so you should remember that. And then the phase we calculate like this. So it's basically the phase of the IL average minus the phase of IL average star reference. Okay, and so this way what you can do is you can give this frequency every time. So you can change this frequency every time. So like you can give 1 hertz, you can give 2 hertz, you can give 10 hertz, you can give any hertz basically you would like to have. You can give 15 hertz, you can give 100 hertz, and so on. Okay, so what you do is you basically give the different frequencies at one time, wait for steady state to occur, and sample the signals using data logging, and then you do FFT of those signals and get the gain and phase for those gain and phase for the frequency, the harmonics present in the system, and you can find these the actual gain and phase for your command tracking plot. So this is our command tracking plot. And once you have these, once you have the many datas, so you can basically plot them using plot functions. So you can basically plot all the graphs. Like you can get the graph by just plotting the points which you get in this table. Okay, so this is how I have obtained the Bode plot, but there are many tools which you can use to get the Bode plot. But I like doing this way because this is in this way you can test your system at particular frequency also, and it works for all the time. And there are some tools which works for just one cases, and it does not work for all the cases. So I prefer doing like this, and the method which this I call is like single sign test. Okay, so why single sign test? Because in one moment I basically give one frequency or one harmonics component in the reference, and then I try to do FFT of those harmonics in steady state to get our gain and the phase value. So it means in one simulation we basically get like just one operating point, and then we have to run the simulation again to get another operating point. So this takes time, but it's more accurate. Okay, so now we can see the further part of the MATLAB script. So here this value is changed to 1, and once it is changed to 1, so these are the frequency values for which I would like to run my simulation. And then you can see my my simulation runs runs like equal to the number of values which we have in this F range. And then basically we run this model using this command. Okay, so I try to change the t runtime just to optimize the time, and this is the command which runs the Simulink model for one frequency, one harmonics frequency, and then using these signals we sample the data log value which we saw. So you can go back and see in these controls we have this data logging blocks. So these are data logging. So we log these data, okay, and then so here we have sampled these signals basically. From the Simulink, we have sampled the signals. So you can sample the signals like this, and you can see the further sampling of the signals. Okay, so we sample for all converters, and then I have created a MATLAB script, so which I'm not going to explain you how it works. But what this does is that it does the FFT analysis of the reference and the actual value, and then it gives you the gain and the phase. So okay, so it gives you the at the end gain, phase, and the corresponding frequency. So this is the same frequency for which we have added the harmonics in the system, and we run this for loop until we have we run this for loop for all the frequencies for which we would like to have the command tracking values. And then at the end, what we have is we have saved these values, and then we do the plot. So this is how we do the plot for the gain. And then in the bottom, if you scroll in the MATLAB script, you will find for the phase. So in the lower section, there is a code which you can run to get your command tracking plot. So I'm not going to explain that. You can look into the code by yourself. Okay, but these are the main steps which is used to get the command tracking plot. And once you run the MATLAB script, so once you run the same MATLAB script by keeping this variable command tracking plot on equal to 1, then you can for sure you can set the bandwidth for tuning. So you can see that for tuning the bandwidth, so here we have in PI tuning, so you can change the bandwidth of your current controller. Okay. Okay. So this is for bandwidth 100 Hertz. And so this again, I just chose it randomly. So no one told me to choose this. I just chose by myself. And you can see these are the command tracking plots for the buck converter, buck boost converter, and buck boost converter. And we have our command tracking plots for both continuous time domain implementation. So the red curve means continuous time domain implementation. The blue curve means the discrete time domain implementation. And you can see that for both for discrete time implementation, the bandwidth gain is very close to 0.707. And it is very close to 0.707 for all the converters. And we can see that for discrete time implementation, our tuning is more accurate than continuous time tuning, because for continuous time tuning, we see the gains are a little far away from our 0.707. Okay, so this is for 100 Hertz tuning, and we expect our the phase difference as 45 degree. So which is also close to minus 45 degree. So this is not exactly the same, but it is close. And you see these deviations between the actual control time implementation using discrete time domain and in continuous time domain. So we have these variations because in discrete time domain, your switches, basically the switches in the system, they are working in a discrete time domain because switches do not. So the switches in the DC-DC converters, they are basically analog for the DC-DC converters. So they are not like a continuous voltage source signal. So we get the switched voltage signals. So this PWM implementation makes our system more into discrete time domain. And so using continuous time implementation, we would have some errors for sure. And there is another reason that that computing the mean value. Okay, so the computing the mean value. So let's go here. So computing this mean using this mean block, this introduces delays in the system. Delays in the system. So in continuous time implementation, we have used this mean for delay to compute the average value. You can also use double sampling, that also works. But if you use like this, then this introduces delays in the system. So this delay and then the discrete. So that delay and And due to the switching behavior of DC-DC converters, what we see is our continuous time implementation is not as accurate as DC-DC converter, discrete time implementation. And in discrete time implementation, the switching behavior of the converter is also taken care, so it works better than your continuous time implementation. So this is for 100 Hertz. And now you see for 400 Hertz, and here we can clearly see the difference between the continuous time and discrete time implementation. And now you can see your discrete time implementation gain is very close to 0.707, and it has tuned nicely. But for 400 Hertz bandwidth with continuous time implementation, you see there is a significant difference between the intended bandwidth and the actual bandwidth. Okay, so if you see the bandwidth for this for the continuous time domain, then we have to project on this axis, and it's like 1, 2, 3, 4, 5, 6. So it is around 600 Hertz. So you can see we wanted to tune our bandwidth around 400 Hertz. Now the tuning using continuous time domain is like around 600 Hertz. So which is not the correct tuning using expression. So now you can clearly see the main advantage of implementing the control in discrete time domain. So in discrete time domain, if you implement, you are already taking care of your switching behavior of the converter, and then the additional delays in the system by computing the mean values is also eliminated. And there is another third advantage, that you just need to sample the signals at the two extremes. Okay, so you don't have to do many samplings. So you can also use some cheap microcontrollers which can work on the less sampling time also. Okay, so these are the main comparison between the continuous time implementation and discrete time implementation, and probably these behaviors you do not see in the step response. So getting this Bode plot is also very helpful, and you can understand your frequency response of the system very clearly using command tracking plot. And okay, now it's time to run the MATLAB Simulink model. So let us go to the MATLAB simulation. So if you try to run this Simulink model, then you would see some error, and it is expected, because it says that that this variable is missing, like this variable is missing, and like that there are many variables. So the very first thing you should do is you should run this MATLAB script, and you can check the settings again by yourself. And so this is one thing, like the bandwidth of inner current controller, and then this setting also you would like to check. So if you want to run if you want to just do the time domain analysis, it means the step response, then you should make this 0. And as I discussed in the slides, that if you make this 0, you just do the parameter initializations, and your simulation does not run from this MATLAB script. And now you can see there are a lot of variables initialized here. And if you try to run the model now, so let's run it. Okay, so now it's compiling, and okay, doing some initializations. And here we go. So now the same Simulink model is running. And this is the same time domain response which I showed you in the slide, where we have given the step response, and you can see that how the actual inductor average current tracks the reference inductor average current. And this is the positive reference current, and after some time you would see the negative reference current also. So let's wait for that time. So here we have the negative reference current. So the reference current has switched from 70 amps to minus 70 amp, and again we can see the same characteristics which we saw in our slides. And here you can see that if you zoom in, you can see that the discrete time implementation, your signals are changing in a discrete manner, and with the continuous time signal, the mean value is changing in continuous time manner. Okay, even you can see it here. So here also you can see the signal changing in a discrete time fashion. Okay, so this is about step time response, and I would like to stop this. And so let us see your so when you run the model, this scope automatically opens and you see this result. And if you do not want that automatic scope to open, then you can simply go there and just uncheck this option. So if you uncheck this, so when you run the simulation, then this will not open automatically. But I would like to keep it like this. And now let's see the instantaneous inductor current and duty cycle, also how they vary. So this is for buck converter, and as I said, you have two scopes for your continuous time signal implementation and then discrete time implementation. So let us see the continuous time signal first. So if you open now, you also have your inductor average current and your instantaneous current. So this is your yeah, so we have both instantaneous and average current, and here you can see that how the instantaneous current is rising. So this is expected. Our instantaneous current will have some ripple on it, and so our instantaneous signal has a lot of noise, a lot of ripple, but our average current has a less ripple, which is also expected. Okay, and yeah, and this is our duty cycle and carrier waveform. So let me zoom in, and you would see that if I want to zoom just one cycle of carrier waveform, so this is our carrier waveform, and okay, so hopefully I can write. So it seems I cannot. So this is our carrier waveform, and for so you can see it's a switching frequency from here, and then this is the green curve is our duty cycle, and you can see how our duty cycle changes during the transients, and then it goes to the steady state value. So this is about buck converter in continuous time with the continuous time control implementation. And now this is our signal with the discrete time implementation, and you can already see this also looks similar, but I would like to mention that for here we do not use the mean block to sample the to get the mean average inductor current. We just do the double sampling, and just to show you the double sampling, so you can we can just see the scope in this way. So now this, from here you can clearly see how the double sampling is working. So this is your carrier waveform. In the lower scope we have the carrier waveform, and then you can see the average inductor current is updated. It is updated only at the extremes. So at this upper extreme this value is updated, and at the lower extreme this value is updated. So yeah, so the average inductor current so we have used double sampling to sample the average inductor current directly from the actual current signal. So we do not do any processing to find the mean value. Okay, and also further you can see in the transients where you wanted to change your reference current from high value to the low value, your duty cycle jumped to a low value, then slowly it comes to the steady state operating point. So this is because of our transients, and yeah, so this is expected so that we have the smooth transition from one reference value to another reference value. So this is for buck converter, and you can open again the same thing for your boost converter, and you can see the signals for both continuous time and discrete time implementation. Okay, and this is for boost converter, and same way you can go back and look into for the buck boost operation. Okay, so I would leave some work for you, so that you should go through this model very carefully, and then you can see the importance of each implementations which is being done. And now let's talk about how you get the body plot. So the very first thing you should do is you should change this command tracking plot on variable to 1. So if you do this, and then what happens, this is 1, and so this is the so this comes into else part, and this in else part, this all computations, simulation running, FFT analysis, and getting your plots is there. Okay, so yeah, so once you make this 1, then what is going to happen, based on these variables, your simulation is going to run. And and if I want to run the simulation for these many frequencies, then for sure it is going to take several minutes. So I'm not going to run for this whole frequency. And further, if you want to run your Simulink model with the higher, basically with the lower Simulink time, then further it is going to take more time. So what I'm going to do is just to show you the results, how it is going to look. So I'm just going to make this the T Simulink 100 times less than switching time, but originally it is 500, like it is 500 times less. And for the frequencies, I'm going to choose some frequencies. So let's say 1, 10. I'll just choose some frequencies so that you can see how this thing works. So let's say 200 and 300. Yeah, so I have chosen 6 frequencies. So what is expected that our Simulink model will run for 6 times. And yeah, so now you can see some lines or some commands working in the workspace in this command window, and you can already see I did not go and run hit my run button in the Simulink model, and now it's still but your Simulink model is running. So now the Simulink model is running from the script, and you can see that this is red curve is reference value. And now we have added harmonics into the system. So this is 1 Hz harmonics added, and you can see that your reference value and actual values are tracking very well. Yeah. Okay, so this is for time. This is for frequency 1 Hz, and so now it is going to run for the frequency 10 Hz. Yeah, so it is going to look like this. So since it is done for the 100 times less the switching time, so you see some distortion in the waveforms. But if you do it like 500 times less than the switching time period as a sampling as a Simulink sample time, then these waveforms are going to look much better. And this is the average values. And if you want to see instantaneous, also you can see the instantaneous values. Okay, so let's see the instantaneous values. So here also you can see your instantaneous values are also changing in a fashion of sine wave. Yeah, so this is also expected because your average is varying in the sine fashion. So your ripple average will like this. Yeah, so this ripple is also going to change in a sinusoidal function. So I have done a lot of work to make this model and to make these scopes looks nice, so that you can read this when I'm making this video. So I have done all the beautification work for you, and I have tried to make everything automized. So you feel free to do add scopes wherever you want. You want to do some change some blocks, you're free to do anything you wish. I'm not going to say anything, and I actually would appreciate if you do some changes in the block to get more familiar with the system. Okay, so once you run the MATLAB script, yeah, so you would see some waveforms like this. Okay, and as you can see, the waveforms are not looking as nice as in the presentation, but this will look nice if you change this the settings. If you change this setting to 500 again and then run the model, then it would look much better. But I think we do not have much time. We should not spend much time on making this video. There's one more thing I would like to mention, that for my simulation, I try to use the actual circuit for validating the control. I would have done using the average circuit diagram, but you know, your control should work in actual circuit diagram, and your tuning should be perfect in the actual circuit diagram with the actual physical system. So if your control is validated using actual hardware circuit, then you can be 100% confident that your model is also going to work with the average circuit model. Okay, so you should actually be more interested validating your control in using actual hardware circuit, yeah, you should actually not only validate your circuit using average circuit model. You should also validate your circuit using your control and circuit using actual hardware circuit. Okay, so I think this is all about this video, and I would like to thank you for staying this long with me, and feel free to comments, ask questions, and if you enjoy watching this video, then please like, share, and comment, and see you next time. Bye bye.